Hello, my name is Michael Koenigsman, and I'm an application specialist at Keysight Technologies. This series of tutorial in OMA will give you an overview of the common errors when analyzing the constellation diagrams of the coherent test signals. In this video, you will learn how to identify quadrature error and get to know its possible root cause. A quadrature error describes the orthogonality error between the I and Q components of the complex modulated signal. Ideally, I and Q signals should be orthogonal, meaning 90 degrees apart. The constellation diagram on the right-hand side describes a constellation distorted by a quadrature error. A reference constellation is shown as 4 gray crosshairs in the constellation diagram. They mark the positions of the expected constellation points. The enlarged section reveals where the quadrature error is measured and that there's no 90-degree angle between the I and Q signals in our example. The optical modulation analyzer can be set up to measure the angular error in the optics properties window, shown below the constellation diagram. The OMA reports a quadrature error of minus 19.9 degrees, which means that the angle between I and Q is only 70.1 degrees instead of the desired 90 degrees. This means for modulation formats with square constellation diagrams such as QPSK, the expected square in the IQ constellation diagram is distorted to a diamond shape. Typically, the goal is to achieve an error in the order of a few tenths of a degree. The quadrature error could stem from an improper bias voltage setting of the phase modulator part of a Mach-Zehnder modulator. Here we see a simplified block diagram of a Mach-Zehnder modulator. The bias voltages of the I and Q branches are set up to the minimum power transmission point, often also referred to as the field quadrature point. In the field and power output characteristics on the right are the 2 red dots. The voltage UPM of the phase shifter or modulator in the Q branch of the Mach-Zehnder modulator is set to maintain a phase offset of pi divided by 2 between the I and the Q signal. If this condition is not met at the phase shifter due to an unfavorable bias, it results in a quadrature error, which can be best seen in the constellation diagram. As you can see, the spectrum in the upper right corner shows no change due to the quadrature error. On the left of the 2 constellation diagrams, you can see the effect of a quadrature error of 20 degrees plus minus. The quadrature error and thus the display is usually static. For illustration purposes, the quadrature error was varied dynamically over time. On the diagram on the bottom right, the quadrature error over time is shown as a strip chart. A small note that only the absolute value of the quadrature error is displayed, unless a BER measurement is active and the OMA software can be synchronized with a PRBS. So this is all you need to know for identifying and to rectify quadrature error. If you wish to learn more about the capabilities of the OMA software, please visit keysight.com. Don't forget to subscribe to our channel and stay tuned for the next tutorial. Thank you so much for your attention, and goodbye.